Hello and welcome to the last review session for Calculus 3208 for Unit 7. One unit to go and that's Unit 8, and it's a fun one too, but this is the last session for Unit 7 and we're looking at areas between curves. So we've already seen how to calculate the area between a curve and the x-axis. So what do we do if we're trying to find the area between a curve and some other curve that's not necessarily the x-axis? Well, sounds like fun. Let's have a look. Okay. So we're going to start by looking at, first of all, a formula. And basically everybody loves a formula, don't they? They can just stick some numbers in a formula and get an answer instead of having to think about stuff. Well, you still have to think about stuff. I'm sorry. So we're going to look at a formula for the area between two curves. And then we're going to look at a few examples of how we compute the areas of enclosed regions. So regions that are enclosed by two or more curves, etc., etc., etc. Let's get started. So areas between two curves. So this diagram is one that's actually from your textbook. But what this diagram says is it takes one function whose graph is given here. So y equals f of x is the blue curve. And then the other function, y equals g of x, is this black curve that's given down here. And we want to find the area that's in between those two. So basically, this area that we called S in here is the stuff that's in between both g of x and f of x on this interval that goes from a up to b. Okay? So to find that area, here's how we're going to think about it. We're going to think about taking all of the area that's under f of x. So I'm just going to trace that out if I can. So the area that's underneath f of x would look, boy, I'm terrible at drawing graphs, but it would look kind of like this. Okay? So let's take that for a second, and there's all the area that's underneath f of x. And now what we're going to do is we're going to think about the area that's underneath g of x. So the area underneath g of x would be everything that's inside here. So in between there and then also all the way across there. So that's the area that I just traced out there. That's the area that's underneath g of x. And so the area that we want is all the area that's underneath f, but I'm going to subtract away the stuff that's underneath g as well to leave me with the area that's in between those two curves. And that area in between the two curves is just this business right in here. So I start with all of f, and then I throw out an amount that's equal to how much is under g. Okay? And that'll give us what we want. So start with all of f, throw out an amount that's equal to what's under g, and we'll be good. So basically what that would mean then is I'd want to get my area S that we're looking at here by taking the integral from a to b under f and subtract the integral from a to b that's under g, and that should give us the proper area. But since we have rules for integrals that we saw before that say the sum or difference of an integral is equal to the integral of the sums or the integral of the difference, then for those two we can combine them all into one integral that's just the antiderivative, or sorry, the definite integral from a to b of f of x minus g of x. And this is going to work as long as f is the function that's above g. Okay, so if they flip around or do different things, we might have to accommodate in different ways. But for now, for our purposes, we're just interested in finding. Take the top one minus the bottom one, and then you go take your integral from a to b, and you're all set. So let's get down to business. Let's look at our first example here. So it says compute the area of the region shown. So that's this blue stuff that's in here. So if I want to find that area, I've got to take the integral from one endpoint a up to b. So a here would be this 1, and b would be this 3. So I'm going to go from 1 up to 3 of the top curve minus the bottom curve. So I don't care if you call them f or g or spaghetti and meatballs, but I'm going to write them in there as the top curve, which is 1/2 of x cubed minus 5/2 of x squared plus 3x plus 3, and then we have to subtract the other curve, which is negative x squared plus 4x minus 2, and all of that multiplied by the magic dx, and that integral should give us the right area. So since this is a polynomial with terms up to cubic, and this is a polynomial with terms up to quadratic, before we actually integrate and have to do anti-differentiation on, well, we've got 7 terms here. If we combine like terms, that'll save us a bit of work, so let's try that. So let's go from 1 up to 3. There's nothing to combine with my cubic term, unfortunately. So that's going to have to remain as 1/2 of x cubed. I have 2 quadratic terms, though. I've got this supposed to look like a 5 over 2. It's a negative, and I've got, this is going to turn out to be a negative, so a positive x squared. So minus 5 over 2, and then positive x squared is going to give me negative 3 over 2 x squared. A bit of mental arithmetic. And then for x's, I've got a positive 3, and I'm subtracting a positive 4, so that's going to be a negative 1x overall. And then I have a 3 plus a 2 because I'm subtracting a negative. So all I have to do now is integrate this polynomial with respect to x on the interval from 1 to 3, and I should know the area that's trapped in that funny looking region there. What does that look like anyway? I don't know. Think about it. So let's integrate here. So 1/2 of x cubed, so that's going to be x to the power of 4 over 4 times 1/2, so that's an 8. And then we're going to subtract, let's see, x cubed, so we're going to have an x cubed here, and then we're going to have to take 3 over 2 and multiply by 1/4, so that's going to give us 3, or sorry, multiply by 1/3, aren't we? So that's just over 2. That's nice. And then we subtract x squared over 2 and add a 2x. And all of that has to be evaluated on the interval that goes from, of course, 1 up to 3. So we fill in our numbers and hopefully can manage the arithmetic. So this will be 3 to the power of 4 over 8, subtract 3 cubed on 2, minus 3 squared on 2, plus 2 3s are 6. And from that now, we have to figure out what that stuff is, and then subtract. All of those x's and stuff are going to be 1s now. So it's 1/8 minus 1/2, minus another half, and then plus 2. Okay, some arithmetic to do now. So 3 to the power of 4 should be 81 over 8. And then minus, looks like 3 squared over 2 should be 27 over 2. Minus 9 over 2 plus 6. And over in the other set of brackets, there's not much to compute, but I'm going to combine my 2 minus 1/2s. So this will make subtraction with 1 over 8 minus 1 plus 2, and I can combine those as well. That's nice. So let's see what we're going to get next. We're going to have and I'm just noticing a little mistake that I made here, so I'm going to go back and fix it quickly. Right over, let's see, and some of you are probably watching this saying, oh, we finally found it. We were having fun laughing at him. Right up here, when I had a positive 3 and I was subtracting a negative 2, that should make 3 plus 2 should be a 5 there. So that should be a 5, making that a 5x, and making this number right here a 5 as well. So that makes this one a 5. Sorry about that. My apologies. I am now corrected, though, so everything should be fine there, unless I made 10 other mistakes that I just haven't realized yet, but we all do it. So let's see. This is going to be 81 over 8, and 27 over 2, and 9 over 2 makes 36 over 2. So they're both negative, but they're both divided by 2. So let's say subtract 18 there. Does it sound like it sounds about right? 18, and oh my goodness, I forgot to change this number because of that one as well. So this number right here should be a 15 now instead of just a 6. So sorry about that. Compounding from that last error, this one here should be a 15. So we'll fix that one up too. There we go, that's better. So what we're going to have now is 81 over 8, and we just decided that that was 18, and then plus that 15, it was a negative 18 actually. So negative 18 plus that 15 that we have should give us a positive, sorry, negative 3 there. And then from our other one, we've got 1 over 8. Oh, look, we can combine those two, plus a 4. Okay, so let's put all these together at one time. I think it will make it a little bit smoother. So let's go back and erase this and destroy some of the evidence of my earlier mistake. So we get rid of that, and what we're going to have now is, let's see, 81 over 8 subtract 1 over 8 is going to be 80 over 8. I kept those apart because I knew they had the same denominator. And then negative 3 minus 4 will give us a negative 7. Oh, wow, this is nice. So it's just 10 minus 7. So we have an area that's equal to 3 units exactly. So this area in here is 3. Nice. Okay. Glad I fixed that before it got too far. Next. Example 2, compute the area of the region enclosed by y equals 3x minus 2x squared and y equals 3x squared minus 2x. Okay, well, here's a problem. Where do we go from here up to here? What are our values of a and b going to be? Okay, so this is a common type of thing to get. If you're not given values, but you're either given a graph where you can figure out that the two curves intersect, then the region enclosed by those two curves is going to start at one of their points of intersection, like this one over here at A. Looks like that one's going to be at 0, 0, but we'll have to verify that as well. And this other point over here at B, and we don't know what this is yet, so we're going to have to figure that one out. All right, so let's go ahead and find the points of intersection. So to get those, we're going to take f of x equals g of x, or they're not called f and g, let's just make them equal. So 3x minus 2x squared equals 3x squared minus 2x, and this is not going to be bad to work out at all. Put all the terms on one side because we're quadratic. So we've got 5x squared minus 5x, so we can factor out a common factor of 5x. We have x minus 1, giving us roots at x would equal 0 or x would equal 1. So we did verify that that one is at 0 and this one is at 1, and since for the limits on our integral we don't need to know what the y-coordinate is, we don't care, so we're not even going to figure it out. Okay. So now what we have to do is we have to find that area by computing the definite integral that goes from 0 up to 1, so nice friendly numbers to work with, of the top curve minus the bottom curve. Now the red one is upside down for a parabola, and the blue one is facing up the right way. So which one of these two curves is going to be the one that's facing upside down? Well, the one that's got a negative x squared term. So that's going to be the curve that's on top, so I have to put that one first, subtract the other one. Otherwise I'll get a negative answer and I'll get confused about area. So this is 3x minus 2x squared, and I have to subtract the upward facing one, 3x squared minus 2x, like so, dx. So let's put all this together to combine like terms. We're going to have negative 5x squared there, and then plus, looks like 5x. Okay, so we've got negative 5x squared, whoops, plus 5x dx, like so. So we'll do the anti-differentiation business, and that will give us negative 5x cubed over 3, and plus, looks like 5x squared on 2. And I know I have to evaluate from 0 to 1. So let's do the evaluation bit now. If I evaluate that at 1, I'm going to have negative 5 times 1 cubed over 3 plus 5 times 1 squared on 2. And I'm going to cheat and say since both of these have x in the numerator and I'm evaluating at 0, I'm just going to end up subtracting 0. So that's going to be minus 5/3 plus 5/2. So let's see, a denominator of 6 would be negative 10 over 6 plus 15 over 6 gives me a final answer of 5 over 6. So the area of that enclosed region in here is 5/6. That's pretty cool. I don't know, what shape is that? I have no idea. A weird wiggly thing. All right. Compute the area of the region enclosed by y equals the square root of x and y equals x squared. So two old friends, and we should know what both of those look like from all of our studies and our other math courses. So let's see. If I think about y equals x squared, or sorry, square root x, that's principal square root, so there's no negatives. That only really exists over here, so I don't even need to look at the other side of my parabola, just the side that's over here for y equals x squared. So there's x squared and there's square root x, and this is obviously going to be the region in here. And we could solve this as a system, but I think it's probably pretty safe for us to say we know that they're going to intersect at the origin. And over here, if I go over 1, I'm going to go up 1 unit on both of those. We should know enough about those curves to know that. So I'm trying to find this area in here. So again, we have an integral from 0 to 1, and the top curve is the square root function, and the bottom curve is the square, and that'll tell us the area in between them. So we've got the integral from 0 to 1 of x to the power of a half minus x squared dx. So putting that together, I've got x to the power of 3 over 2 divided by 3 over 2, or multiplied by 2/3. Subtract x cubed, on 3. And that goes from 0 to 1. So evaluating at 1, I'm going to get 2/3, subtract 1/3. And evaluating at 0, I'm going to get 0. So it looks like the magic answer here should be very simply 1/3. Interesting. Same as the area underneath. X squared from 0 to 1. Cool. All right. Makes sense, I guess, if you think about symmetry, though, because that's a square box, and it looks like we took a pretty symmetric piece out of the middle. Neat. All right. So the your turn question. The region R is in the first quadrant, and it's bounded by these two monsters. So it says sketch R and label its left and rightmost endpoints. So it gives you a hint that you got to find them. Then determine the area of R, which is the region that's contained in between them or bound by them. Okay, so here's the solution for that. So if you worked all that out in its gory details, you got something like this: 9 over 2 or 4.5 for area. I hope you're getting the right answer. If not, I hope you're figuring out why you're not getting the right answer. And then we'll jump along here and take a look at some summary business. So let's summarize the last section of Unit 7 here. The area between two curves f and g, where f is the greater of the two above it on the graph. It can be computed using this formula. So there's the formula that we figured out at the beginning. This formula is straightforward to use if the endpoints a and b are given. Okay, when the endpoints are not given, not then the endpoints are not given, but when the endpoints are not given, we need to compute them by finding the intersection of the two curves, and typically this is most easily done by solving where f of x equals g of x. That gives us our intersections, and then we know where a and b are. Okay, so good stuff. Hopefully you got something out of that, and hopefully your studying is going well, and you're preparing yourself well for your final exams. If you have any questions for me concerning the calculus, please post them up on D2L. Have a good day.